Muito bem, vamos então para o segundo curso da tarde. Na verdade, esse é o mini curso número 2 do programa temático, a ser ministrado pelo professor Bernd Hofmann, da Universidade de Chemnitz. Please, Professor Hofmann.
Thank you. Yeah, first, I'm very happy that so many people are here. It is rather late. Sorry that I am a morning speaker, not an evening speaker, and so I'm very sorry about this. Maybe it will be seen. My last lecture on inverse problems given in the last semester started at 7:30 in the morning. So you see, hard life of the students in Chemnitz. So some words which don't know it. Chemnitz is a university in the east part of Germany, about 200 kilometers south of the capital Berlin. And yeah, there is a good motivation for coming here. I very thank the IMPA for invitation to this lecture course. The real hard motivation is that we have a joint conference. Since 2002, our research group organizes a Chemnitz symposium on inverse problems. It's a small symposium, in particular for the young scientists. And from time to time, we go abroad or we go on tour. And so we have been in China, we have been in Australia, and now we have the honor to come to Rio in this year. And after 2 weeks, we will have this conference, specially organized by Professor Antonio Leitao from Florianopolis. And yeah, and so I'm happy that I have a chance to give 3 lectures here in the series. The name of the lecture is written here. It's included in the thematic program, parameter identification in mathematical models. And you see the title is Regularization Methods in Banach Spaces. But you can be sure that I will not speak only about Banach spaces. It's only a title. I would like to give you some of my ideas about inverse problems at all around, and also some aspects which are interesting in our research. Couple of years it works, and yeah, maybe some words about inverse problems. Why are inverse problems interesting for us, or for me? I started thinking about inverse problems in 1976, very long time. And in this time, nobody said inverse problems. There was ill-posed problems. And so I can say today, if inverse problems would not be ill-posed, they were not interesting for me. The phenomenon of ill-posedness is the phenomenon which is interesting for me, and I always, in very different facets, I considered this phenomenon, and I want to give you some points here. Maybe it's very yeah, stupid for you, but maybe some points are interesting too. In my first lecture today, I want to give you some 4 exactly examples of practical problems which were under consideration in our group in the last years from practical point of view. And I will not go into details. I will only give the examples with some aspects, and then I will come to the mathematics behind. And the mathematics behind is interesting because you need, and this is also an interesting fact for me, therefore I stayed in this inverse problems community since 30 years. There are so many different fields of mathematics which are necessary there, starting with analysis, numerics, optimization, and stochastics. My 3 lectures will not contain too much stochastics. I will consider deterministic models. Of course, we have also done some stochastics aspect, but yeah, I haven't it here in the slides. Some words about the history. You will see many names. You heard it. Professor Baumeister gave a long series of talks, and so I hope I will not repeat all or repeat too much. Yeah, there are many names. And the ill-posed problems, which is the original, I think, were started, as I think, in the beginning of the 1960s. There are papers in 1962 from the school of Tikhonov in Moscow. And yeah, he had a big group. The situation in Russia was there that one could have 500 people who thought about these things. And so I think for the non-Russian speaking people, the monograph by Tikhonov and Arsenin in 1979 or so was the first one could read really in the Western world about this. Yeah, then yeah, I had to read it in Russian, unfortunately. I could never speak Russian too good, but it was enough to read it. And in the 1980s, a couple of interesting monographs were published on ill-posedness, on inverse problems. And the word inverse problems started to come up in the 70s and then in the 80s. One is the monograph by Johann Baumeister. One is the monograph by Chuck Grudge in Cincinnati. And so I was interested in reading all this. And I read the Russian and I read the English literature. And in 1986, I published a monograph in Teubner Publisher and tried to bring the things together. But if I read this book now, I say, ooh, I did nothing. I did not understand the things. But it's clear this was the first phase in this point. And many colleagues started. Phillips from the United States was one. In the Western community, they say Tikhonov-Phillips regularization. Really, Phillips published a paper in 1962, I think. So, but he had not a group of 500 people. So the Russians brought, let's say, 1,000 publications in the last 30 years there. And when the Soviet Union collapsed, then the system stopped anyway. And so many people went away and work now, for example, in the United States and Israel and so on. So this was a really interruption there. And now, today, yeah, the focus of inverse problems is more to Europe, more to US, more to South America, and IMPA is a very important institute for making applied mathematics. And my favorite country, besides Germany, is Austria. I'm very Austria-affine. And Heinz Engel, one of the big names of the inverse problems community, Heinz Engel was, for me, one of the most important person in this group around, in particular Ottmar Scherzer, who is now a very, very important person there. And so all my notation will be really Austrian notation, as you will see. There is a Russian notation, Austrian notation. I will call you very shortly, which is the difference there. And so this only for the introduction. Now, some words about the general things, some examples, and in the second part, it's very late, but I hope you can accept this. I will speak about a concept of ill-posedness. Nobody in the literature will like this or will see this, but I hope I can convince you that it makes sense to write this down once clearly. So this is my goal there. And and more I haven't for this day, and I'm a very big fan of a mouse there, therefore I use it now. In all, doesn't work here. It works. In all my lectures, at the end, you can find relevant references with focus on the points I discuss here. You can, in principle, download all the papers if somebody should be interested from my homepage in the original form or in a preprint form, which in order to accept the things which publishers do. So, and therefore, if you are interested in doing so, please ask me, please write me an email or so. If anyone, there is some question around this point. So I can go back, I think. And I can start with some words before. The goal of inverse problems consists in the identification of unobservable physical quantities, I say causes, and which you have are data of dependent observable quantities, effects. So this was a trivial assertion, everybody knows. But for me, in particular for our students, it's important to know what is the specific of an inverse problem in its intrinsic form. From my point of view, the specific is that the mapping from the cause to the effect is moving. I say it's moving in a very general sense. So what does it mean? You have a cause, my left hand, and you have a cause, my right hand. And these causes are well distinguished. What happens if you have a forward operator, a forward map, which is moving? It's moving denotes that information of the difference gets lost through this process, and you end at such situation, which I show here, and then you have data errors. So, and this is the recovery problem which you have. But the effect of forward operators moving is the phenomenon which brings the ill-posedness. And one can express it by mathematical terms. I will try it in the second term. So, yeah, they tend to ill-pose. Let's say it very, very rough here. All you know it, that means that, yeah, small changes in the data may lead to arbitrary large errors in the quantity to be identified. And I will do it a little bit more precisely. And I will, in all my 3 lectures, I hope it's relevant in all the points, I will have 2 different problems, 1-star problem, 2-star problem. The 1-star problem is the problem of linear ill-posed problem, which means nothing, that A is a forward operator, which is a bounded linear operator mapping between abstract spaces. And in my lectures, at the moment, we have only infinite dimensional Hilbert or Banach spaces. That means, yeah, my lectures consider the infinite dimensional case. And so you say, but now you must come to discretization, you must come to iteration, you must come. Well, but we just heard a nice lecture about, we have many other lectures here. I stay in the infinite dimensional case, and all the other things which then come are very complicated, maybe too complicated for me, but I came from the other side. I started with the discretization, and then I came to infinite dimensional spaces, and I see the infinite dimensional spaces are not so simple to handle, so please allow me to go in this way here. Linear problems, if you see this A, then you see linear problems. And nonlinear problem, here you see the Austrian notation. I will use as F as a nonlinear operator, nonlinear forward operator, mapping the to the object to be identified to the object which characterize exact right-hand sides and which are perturbed with data. And you have the data and you have to solve the. That means in my simple model here, inverse problems is solving inverse problems denotes solving such abstract operator equations. That means you have it with linear or nonlinear forward operator. You have it with exact right-hand side. And, of course, you have not the exact right-hand side, but you have only noisy data. The noise will be always a deterministic noise in my setting. Ill-posedness, we have it in a very rough form now. Ill-posedness denotes, due to this, regularization methods are required. Which means if you do it in a very trivial form, for example, you take the data, you take the forward operator, and you say AX, for example, for the star problem, AX minus Y, let's say Y delta is norm goes to minimum, then you can discretize it and you can solve it. This is the normal phenomenon of colleagues from very different fields who are not well acquainted with inverse problems with the phenomenon. Let me briefly tell a story. There were colleagues from nuclear physics from Berlin. They came to us. They had a very simple problem. They wanted to recover a spectrum of photons, which means different energy, different photons. This is a photon spectrum, but they cannot measure it. For example, in a nuclear plant inside, you cannot measure it. They can only measure a number of electrical impulse spectrum. And so there is a combination between, there is a forward operator, and this forward operator is nothing but a Fredholm integral operator of the first kind. So what did the guys from physics? They discretized it. They took 40 different energy levels, made a discretization, the linear operator, so it was a linear equation system, 40 times 40, and they made minimization, AX minus Y delta, norm to minimum. And the result was as follows. This was the energy, 0 to maximum energy. And this is the number of photons after recovery. And the result was such a thing. So this was 10 to 6. This was minus 10 to 6. And they came to us and they told us, oh, now some of our colleagues really think about the meaning of a number of minus 10 to 6 photons. What can this mean? Can we get, for example, with some effects of quantum mechanics or so, can we find something? This was nothing but a clearly situation that they had an ill-conditioned system. The condition number was 10 to the 16th about, and so this was nothing but this effect. So in principle, ill-posedness can lead to new physical theories, but not always in a very efficient manner. So we took it, some trivial form of regularization, and really we got it in a very good way. I will not go in details, but I will mention this because I have here different kinds of objective and subjective information. Regularization, you know it all, means you take the ill-posed problem and you replace it by a neighboring problem. The neighboring problem is well-posed. And if the neighbor is really a neighbor, which in general means that the regularization parameter is very small, then the bad properties of the ill-posed problem are still a little bit in the neighboring problem. If you have a neighbor of 10 houses away from you, then the stabilization is very fine. You have a stable problem, but this house has nothing to do with your house. So you always have to find a compromise. You have the regularization parameter in very general form, very different forms. So, and yeah, let me say some bad word. In the last 30 years, finding the regularization parameter, there was a very big progress, but this progress was nothing. There are, let's say, 500 papers about this. But from my point of view, since 30 years, nothing happened there. It cannot happen because you have the problem that you have no information about this. If you want to find the optimal regularization parameter, you must know the solution. So if you know the solution, you need not do all the things here. And so in principle, one can try to put some hairs out of the water, but in principle, you have always the same problem. You try to feel about the things, and so, and you land in good or in bad situation. From our philosophy, we have the following. We distinguish objective and subjective a priori information in order to construct such a form of regularization. Very different kind of strategies, of varieties, but in principle it's always the same. What is, in my meaning, objective? Objective if properties which are objective, well known. For example, in my simple problem here, the number of photons is non-negative. It's objective. Nobody has seen negative numbers of photons. As a form, we were successful in this small problem when we said, okay, what do you know about your spectrum? And they knew much. They knew much. They knew that the following. There was a spectrum had such a structure. Not in the negative here. In such a structure with two peaks, and it comes from 0, goes to 0 at the end. And the two peaks were well known, peak 1, peak 2, and they knew, okay, there was a monotone increasing, and as we know, monotonicity and convexity properties lead to compact sets in L2 if you have upper and lower bounds. So this was one of the best ways to handle this here. Moreover, we had a quotient of the altitudes of the peaks, also an objective term from physics. So this is objective. And you should use all objective a priori information in order to handle your problem. Now, at the end, if you have only non-negativity, if you only have box constraints, this is not so much objective. You cannot stabilize it very good. So you need, for regularization, and therefore Tikhonov regularization, we heard it today a couple of times, is a very important point. And Tikhonov regularization is a method which uses subjective information. For example, in the form that you have a penalty added to the discrepancy multiplied by a regularization parameter, and this penalty functional is completely subjective. If you do not know more, you need all your expectation or the expectation of the old engineer, which all he knows, into that subjective part. So if your subjective assumption is completely right, then you can be very successful. If your assumption is not so good, then regularization will fail. For example, in general, regularization penalties are smoothing. That means if you have a function highly oscillating and you have a function which is smooth, then you prefer the smooth one. But if the solution is sinus of 100 times t, and you do it, then you are wrong. And this is subjective. If you do not know it, then you can fail for this. But this is a problem. In addition to the problem of finding the regularization parameter, to finding this objective, defining this subjective penalty is the main problem which you have. And you cannot overcome this. You must live with and say you must accept this. And therefore, you cannot, as for example, the friends from finite element method can make an error measure, and you know how far is my solution from the exact solution. But here you cannot. You have no chance. The answer is, why does it occur? Because the inverse operator is unbounded in linear case, or has bad properties in the nonlinear case. And we will see it a little bit more here. Descriptive regularization is a method which, in principle, preferably uses objective information. For example, if you have monotonicity here, then you can use descriptive regularization. There is a nice book of Anatoly Yagola about all these things, all this descriptive regularization, and it is interesting to read it. It goes into numerical details too. I prefer in my talks variational regularization, Tikhonov type regularization, and you will see here preferably this kind of regularization. And we have seen in Uri's lecture here that many different kinds of penalties can occur from different applications, from different subjective assumptions which are here. For example, do you want to use maximum entropy, or do you want to use BV method? So this is subjective and depends on the background you have it. Another method is singular perturbation, or sometimes called Lavrentiev regularization. Lavrentiev was a professor in Novosibirsk, and he developed also in the 1960s this method. This method is much simpler, but it can only be applied if the forward operator is monotone. I will go in details in my second talk in Tuesday into that. Iterative regularization. We have many specialists of iterative regularization here, and it starts with Antonio. All people know so much about. I will not discuss iterative regularization in detail because, this is a known world and would be too much for the 3 lectures here in this world. As our focus is on these 2 things, and X dagger is also always my exact solution for star and for 2 star. Very briefly, before we start with the examples, this is Tikhonov regularization in my form. In a general way, you have a norm of a Banach space. You have a power P, which is between 1 and infinity here. And this is the Austrian notation for this form. This R will be, in general, in my discussion, a convex functional. And this P, why this P? In Banach spaces, it is often used. For example, if you have LP spaces, then this power P is helpful for constructing the discrepancy in a much simpler form. So I will come back on Tuesday to that form very, very deeply here. Now, a couple of examples, not because they are so important, but because they enlighten a bit the world here. I have 3 examples which are 2 stars, nonlinear, and 1 example, 1 star. And the examples partially are already mentioned here, come from different fields. I start with problem recovery of gas temperature in fault arc test. What does it mean? In our Saxon, Chemnitz is in the state Saxony in Germany. The Saxon Textile Institute does much concerning protective clothes for working people, and in particular exposed to the risk of fault accidents with electric things. And this is the effect. So this is, if this guy does not make all the things right in, for example, 10,000 volt or 20,000 volt, then such an electric fault occurs. And if this has such a shirt like me, he's dead immediately. So these people, because this is a rare effect, but it occurs, they develop clauses for these persons in order, they are burned, but they are not burned level 4, but maybe level 2 or level 1. So this is the question. And the question, from a mathematical point of view, from the colleagues which came to us was, here is the art, electric fault art. What is the gas temperature immediately here? And what is the implication of this gas temperature to this person, let's say, half a meter away or so? This was the problem here. And so I'm not a specialist in PDEs. We have so many specialists in PDEs here, so it's not necessary to have another one. This is the orientation. They make a test arrangement. They have here such a calorimeter. They measure this, and here this is the electrode which is started. The unknown, the X in my form, is the cause, is the gas temperature as a temperature of time. Then, you have this cause, and the effect is what is the temperature which you measure in. So, simple, well-known architecture of the system, and you see this gas temperature occurs here in the radiation term and in the boundary term. So you have it in a very nonlinear way, and in principle, the nonlinear operator, the forward operator, is transforming the gas temperature to the temperature measurements in the calorimeter here. So, and the question is, can we recover this gas temperature in that way? And you see, this is the calibration measurement. In this form, you see it up to 70 degrees. And this is enough away. And the 70 degrees is measurable. And the real temperature is in that way, as you see, after 1 second, you have temperature of about 4,500 degrees centigrade. So you cannot measure this. So, so you try to recover this peak here in that way, and the gas temperature reconstruction in a simple way without regularization has this form. So the engineers do not like this so much. So I was very surprised about, they were not interested in this first part, they were interested in that part, this oscillation, this impossible to have this oscillation. I cannot live with this. I must know how it happens after 15, after 30 seconds. So, you can take your box of all the regularization methods and you can start with, and for example, Tikhonov regularization in that form may have this structure, and you know the temperature must decrease, so you can use monotonicity, you can use descriptive regularization, and you get such form. And if you apply this to the practical textiles, you see with textiles, the temperature distribution is here in that way, unregularized, in that way with Tikhonov, and in that way with descriptive regularization. And this helps a little bit for giving ideas, and they can make experiments with this. And so, the tool, the box of regularization methods can help a bit in order to make that kind of engineer a bit more happy than in this highly oscillating thing. So, not an important example, but from my point of view, one example which shows nonlinear inverse problems. And you need your standard tools, you need mathematics. Another problem came from colleagues from the laser optics in the Max Born Institute of Short-Time Laser Optics in Berlin. And they have read our old papers on auto-convolution. That means you have a convolution of an unknown function with itself, and you measure it with noisy data. And we did it with Rudolf Gordon in 1994, first time. Also, Hans Baumeister has made papers in this time on this. And yeah, we did something up to 1997 with some PhD students of mine, and then we forgot it. So 5 years ago, or 4 years ago, the colleagues from Berlin came to us and said, we have found your paper from 1994, and we have just this problem, just such a problem. Namely, we have a method which is called spider, and this is the table they have. My PhD student was in Berlin, and he worked on this table. It's a very small table with many, many parts, many optical items, and yeah, you see the ray is going from left to the right and again and back and so. And the effect is that really, in order to get information about the characterization of such a short time pulse, note the Max Born Institute makes the shortest time pulses of the world. femtosecond is the length, 10 to the minus 15 seconds. And all the measurement tools cannot handle this because they are too slow. And so, but by autoconvolution, you can find solution there. Namely, in the following way, you can measure by this table this y of s. I have normalized it to the normalized intervals here. And you want to recover this x. This is the characterization of the pulse in an interval from 0 to 1. And you have here, this is the new point. You have here a kernel. And this kernel is nothing but an apparatus function from the table all around. And because of these different ray ways, this autoconvolution is a typical behavior here. And so, in principle, yeah, after 20 years or so, we restarted to consider autoconvolution, but now in a more sophisticated way. Now, our function are function in L2C, complex function. They have a magnitude, they have a phase, they have a norm, and so in principle this is much more complicated. Also, the kernel is a complex function. Yeah, and we did a couple of papers. You can find about 10 papers in my homepage, which give assertions on this kind of problems here. There are many bad points for mathematics. For example, they measure different things. For example, they cannot measure parts of the right-hand side. They are not interested in parts of the solution. They are interested in the phase, and they often only want to measure a phase on the right-hand side. And so, yeah, for the colleagues who like function analysis, it's rather complicated. You have no Banach space for this. This was one of the most complicated situations. But in the first phase, regularization in the already classical form helped. Adapted a priori parameter choices also helped a little bit. And if you see it, the best effect which we had, where this is the phase which was to recover, and this is the phase which we could recover, and you see such a set-off, but this is a phase, and 2 pi is not a problem, because the phase jumps are here in such a 4 points. In principle, they are separated. You can shift it, but you see recovery of such phases not simple. Yeah, phase recovery is a big point in mathematics, but this is a little bit another kind of phase recovery. You see, really, again, you have a forward operator which is nonlinear, but it's a rather simple. It's a quadratic forward operator, a very simple, as you think. But if you analyze this very deeply, you see. I will discuss this on Tuesday. You see all the conditions on structural nonlinearity assumptions, for example, tangential cone conditional, completely fail. All fail this autoconvolution destroys this completely. This is some kind of, the first part and the second part will be multiplied, and so you have no chance to find a nice strategy. For example, in the form of the Genscher-Cohen condition, which is for PDE problems, often identification problem, you can often have it, but here in the simple quadratic problem, we haven't it. My PhD student, Stephen Berger, could show that nearly all conditions on nonlinearity failed for this problem. The only one which was the rest is a Lipschitz continuity of the Frechet derivative. This the only one have, and it's not so much. Tuesday I will discuss the disadvantage of such an effect. Second is away. The third comes. Joseph Zabelli is very specialist here. And yeah, we have still more specialists on this. Yeah, in the 10 years ago or so, under the big cover nonlinear inverse problems, we also discussed inverse problems in imaging, inverse problems in option pricing. 10 years ago, everybody was a financial mathematician. I did not meet any guy who was from statistics or from stochastic, all were from financial mathematics. After the financial crunch, it changed again a little bit. So, and I had the honor to come to this nice conference, Research and Options of George, and it was very interesting. I met very interesting people like Tubire, for example, and it was very interesting for me, and I learned very much. As we do it always, we only discussed a very, very simple problem. I say it's a benchmark problem. Benchmark problem is as follows. Yeah, we heard about volatility surfaces, about the smile effect today, and we completely forgot it and say, I only want to recover the volatility function as a function of time over some interval. And I only consider the option prices, for example, of an European option, of the same time interval, and say, I do all in infinite dimensional spaces. I say, this is a function I am searching for. This is a function I have given with error, of course. And the question is this problem, this benchmark problem of interest? And we had much trouble to find a journal which accepted that inverse problems, ill-posedness effect, and this kind of financial mathematics can come together and can be published in such a journal. I wrote it to a second-level journal, so I do not like such things. And then we sent it, Kress told me, please send it to inverse problems. This is a higher level, and and really, there was a guy from financial mathematics. He asked 72 questions, and we had to put 72 points in order to answer this. Ill-posedness, why? What does it mean? What is helpful for us? And we answered 64. So he said, okay, but there are a couple of questions are open. Please make a further revision. And it's okay, up to one we could answer all, but this one we couldn't. The referee was wrong at this point. But Heinz Engel was organizer anyway, and he told me, then I stopped the process, and the paper was really published. And after this, we could publish a couple of papers in this field. So this was the breakthrough anyway in this form. Yeah, in this simple form, you have the problem of recovery from option prices to volatility in such a way that outside you have the function, I call it a Black-Scholes function. It comes from the Black-Scholes formula with this well-known parts here. This is the cumulative density function. And you see from point to point, you get a result. This is nothing but a Niemitzsky operator, a nonlinear Niemitzsky operator outside. And this S, which occurs here, will be seen nothing as an integral, a simple integration of the thing. So if you write A is sigma squared, S is this integration, then the operator equation 2 star is the forward operator from A to U, is in that form, this Black-Scholes function. And here in the last component of the Black-Scholes function, you have this integral. So in principle, this is a composition of this nonlinear Niemitzsky operator and then, yeah, weakly ill-posed linear operator. And yeah, you can write it, you can analyze it, and we did it. We tried to regularize it, and so. But the interesting point was that you have outside this Niemitzsky operator, inside well-known numeric differentiation, all know. But outside this UBS function, this Black-Scholes function, was very interesting for me. Is this outside problem, this outer problem, is this also ill-posed or not? It's not so clear because you have one-to-one, point-to-point, and yeah, we made many studies also with Peter Mattei in the Weierstraße Institute in Berlin, with my PhD student Romy Kramer. And at the end, you see this is the inner problem, this is the outer problem, and we studied, yeah, you see ill-posedness occurs, but it's an ill-posedness of the inner problem. You can regularize it, no problem. And now the problem, what happens in the outside problem? And you see, if you come near to 0, in practical, this is not a question because you have not an option which only is the next minute. So it's at the moment only a theoretical problem. But this was interesting. What happens there? And you see, you have such a highly oscillating part here in this for a very small maturity. So the question is this ill-posed or not? And if you see, if you go with the delta level to 0, you see this part decreases and decreases. This is nothing but an ill-conditioning effect, but not an ill-posedness effect. So you have outside a well-posed but very ill-conditioned problem, inside well-known but not so strong linear ill-posed. But overall, it's a nonlinear problem. Fourth and last problem in my series. Colleagues from Hamburg came to me and told me, yeah, we have a problem in a PDE problem, which is in the following form. You have to recover such a right-hand side, and the data are a little bit strange. In principle, this elliptic problem has Neumann and Dirichlet boundaries, and they were searching, or they were trying to get information which are not very standard. The information are as follows. You have data of the Dirichlet and of the Neumann type in that form, in a noisy form. And you know, for example, that this norm sum is smaller than some noise level delta. And you try to recover this f function from that. What does it mean? This J delta, G delta is only one such result, one such measuring result, and you want to recover this f from this, and it is very clear that this is in principle not well defined. We have not a forward operator. We have not a well-defined forward operator. In principle, this is set well. You cannot write it as a forward operator. You have no capital F here in that way. But what do you have? You can consider simple the Neumann problem. You can take this right-hand side here, this function to be recovered, you have the Neumann data, and you can solve this problem. For example, in that way, from F, you get such as both should be elements of L2 of the domain omega. And this NF, the solution of the Neumann problem for given such Neumann data. But here, if J is exactly. And same for the Dirichlet problem. Also, if you have the Dirichlet problem, you can solve this problem. You get the Dirichlet operator, and you get this V. So in principle, you can solve this. And if the data are compatible, then all is fine. But it is clear, we know it from Neumann, Dirichlet Neumann map, there is nothing uniquely determined. So in principle, the question was, okay, does it make sense? In principle, you have a solution set of that form. All right-hand sides, F, are of interest, where this Neumann operator applied to exact data and the Dirichlet operator applied to exact data are identical. This is the solution set. And this solution set is infinite, is big, very big. So it's clear this problem is highly underdetermined. But yeah, in regularization, often, since, yeah, for example, the book of Engel.
But this Q norm is the conductivity norm or not? In the previous slide, the Q, the conductivity.
The Q is such a quadratic norm with some matrix here in the. Yeah.
It's not norm.
No. It's a uniformly elliptic thing. Nothing more.
But you know it.
To know it, we know it. The Q is well known. The elliptical operator is well known. But only unknown is this F. No? Yeah, the specialists about I am not so specialist in this thing told me, okay, it's very underdetermined, but we can use, and so this is clear, under the set of all solutions, we have now subjective information, and we take it. And subjective, for example, denotes that we know some initial guess. And the best F, which has the minimum distance to the initial guess, is the function we take. So, and the nice thing is one can show that this solution set is closed, convex, clear it's not a singleton. So, then you can work with regularization theory in the classical form. And it is clear this is really a linear problem. You have a linear problem here. But this linear problem makes some stress because you have not a really forward operator. What happens? What can you do? So colleagues told me, okay, we know the papers of Cohn-Vogelius, well known, and we take such a functional of discrepancy in that form, and we make a Tikhonov regularization in that form, and one can show that the solution, a regularized solution, has this form. And if you have a look at this, you see, this is nothing but a Lavrentiev regularization. It's not a Tikhonov regularization only with specific misfit term, but it's also a Lavrentiev regularization. But the problem is, what does it mean here? You have not a forward operator in a simple way. So this is some form of implicit linear problem which can be solved with Lavrentiev regularization. Now, my Vietnamese colleague, who was the initiator, author of this thing, told me, okay, I can show it. So he showed that all is fine. It's an accretive operator and all these things. And so one can realize this in the following form. You can say, you define this operator and say, solving this were the exact data. You have to solve this operator equation, but you haven't the data here. But the PDE is linear, so you can split the NFJ to N0J and F0 and the D in the same way. And the forward operator you can define as all the things which depend only on F, and not on J and G. And so you have a right-hand side with the rest here, and then you have an explicit linear operator equation, and you can show this operator is really equipped with all properties you have. The forward operator is linear bounded, self-adjoint, monotone, and so you can apply Iterative regularization in the classical way. And yeah, my job in this paper was, we have there a very stupid condition. And if you have this stupid condition is satisfied, then we can show a convergence rate of square root of delta. And the question, we do not know what does it mean. So and after having this, the answer was rather simple. This stupid question was nothing but such a thing. The solution minus the reference element is in the range of this operator. This is just this part. And you have nothing but the well-known source condition, best possible source condition of Iterative regularization. And under this source condition, you all, for example, for simple a priori parameter choice or discrepancy principle, you get square root of delta as a convergence rate. So the problem was only to see that this is a Iterative regularization, and then all was clear. This is an example of a star problem, of a linear problem. And I showed you 3 nonlinear and 1 linear problems. They are not very important, but they are interesting to see what can happen in inverse problem scenario. Last part of my talk today, something about ill-posedness concepts. I think it's important to have an audience to explain this one, because I read from time to time, I read papers on ill-posedness which are a little bit complicated or a little bit strange sometimes. For example, we have a nonlinear operator, and the range of this nonlinear operator is not closed. Therefore, the problem is ill-posed. This is completely stupid, because this has nothing to do with the reality. Therefore, we wanted to write the things down a little bit more clear, and I will do it in a couple of minutes here. The basic of all the things is Adam's well-posedness, ill-posedness definition from the beginning of the 20th century. And yeah, he requires for star or 2 star, as you like, for all right-hand sides, there exists a solution, existence condition. The solution is uniquely determined, well-defined, nothing but injectivity. And the solutions depend stably on the data, which means a small perturbation on the right-hand side lead to small errors in the solution, stability condition. So the first 2 things are nearly clear. The third is, what does it mean? What does it mean if you have non-injective case? It's not so clear at the moment. You have to make it clear in order to understand this. We have tried it to do it. Some remarks. Adam's definition of well-posedness in its entirety can only be of importance for linear equations. For a nonlinear equation, it mostly it does not make sense to have the assumption that all elements of y are in the range y. Exist for Iterative regularization, you have such monotone operator, you have such situation, but in general you have not. So forget the first condition. The second condition, there are 2 situations. You have a situation where the problem is injective, with f injective, or non-injective. In the injective case, all is clear. F to the minus 1 is a single-valued operator, and in such a case, 2i is fulfilled. In the latter case, f to the minus 1 is a set-valued object, and yeah, the 2i is violated. And this f to the minus 1 of y characterizes a set of pre-images. So we have to distinguish these 2 cases in order to get a clear situation. We recall, all you know, you recall the closedness of the range of a linear operator is essential for the well-posedness of linear equations, star. Hence, well-posedness and alternatively ill-posedness are global properties. You have linear problem star, you have well-posed, or you have it ill-posed. We will distinguish things a little bit. So here is all clear, nearly all clear, but the problem begins if you go to nonlinear problems. What does it mean for nonlinear problems? For operator equation with nonlinear problems, the literature uses different concepts, rather rough and only verbally formulated, and so yeah, it is not very convincing. In 1994, I was in Linz with Ottmar Scherzer. We tried to find the definition there, and we called it local well-posedness and local ill-posedness. 15 years, and nobody has taken this. In the last years, there are a couple of papers in inverse problems where for concrete problems, they said, yeah, we can show this is a ill-posed, this is a locally well-posed problem. So it makes sense to explain it a little bit in order to find friends for this also here. Yeah. Stable and unstable behavior of such a nonlinear equation is not only a local property, that means from point to point it can be well-posed or ill-posed, but, and this is interesting, and for me it was not clear. 1 year ago I did not think about this, and it can change from point to point, but it's also to distinguish local properties in the image space and in the solution space. This is completely different, and yeah, I will show this a little bit. If anybody in the audience is interested in this, we have a archive paper with Robert Plato, where we all wrote it with proofs here, and you can read it if you are interested in these things. The first point is local stability in the image space. What does it mean? We have this Adama 3i. And this means, what does it mean, stability? If the problem is injective, all is clear. But what happens if the problem is not injective? What shall we do? And so we can discuss it. What does it mean? We have continuity at one point. So if you know from function of one variable, continuity can be at one point yes, at one point no. So, and the same is here, and continuous means that if the yn go to y, then what happens with that? If you have injective situation, then this is well defined. It is one value, and so this is a clear definition. You have to distinguish in no sense. But in the non-injective case, it is not clear what does it mean, f to the minus 1. So in the most, if you show in the literature, I discussed it also with Radu Botz from Vienna, in the literature of optimization, they always use distances which are symmetric, Hausdorff-like anyway. But for inverse problems, I believe that it is not useful to do it. And so we suggest the following definition. We call such an operator equation stably solvable at one point. Other point can have another property at one point y. If we have for every sequence from the range with this property that this quasi-distance, which also occurs in the 1960s, this quasi-distance goes to 0. What does it mean? Why this quasi-distance? You have this sub-inf. It means if you have a solution set and you do not distinguish different elements in the solution set, you know this is a solution set, I want to have one of the solutions. You have no addition. For example, you can search for X bar solutions, then the solution set is smaller, but it's a solution set. And you are interested in approximate elements. Xn is such an approximate element. So you have no control in your procedure about these approximate elements. They can be such or such. So in principle, you must take the distance between these elements, and because you have no control, you must be the worst case. So this is the supremum, the worst case. Of this infimum, this is the distance. And this is non-symmetric, but for many applications of inverse problems, it makes use. So you have a definition which, from my point of view, is a little bit more adapted than using Hausdorff distances here. Because Hausdorff distances means, okay, you have some information about different solutions, about the value of the solution. Objective a priori information cannot help, but subjective can help. But if you haven't, you can do it in that way. Now we come to linear problems. I like this contribution of the proceedings of the Alpine Conference of Heinz-Engel in 1986. And so Herr Neschet gave a very interesting talk there, and wrote a paper, and he discussed, okay, what is well-posed for linear problems? He says, I say it well-posed in the sense of Nash, if the range is closed. And he, moreover, says, otherwise, ill-posed. He says, ill-posed of type 1 if the range contains an infinite-dimensional closed subspace, and ill-posed of type 2 otherwise. In Hilbert space, all is clear. The second, the type 2, is the compact type. The first is a non-compact type. For example, if you have a Hausdorff moment problem, you measure the moments, you try to recover the density function. You do it in small L2 to big L2 to small L2, then you have a problem of ill-posedness of type 1. It is, in my book, it takes four pages to show it, but it's for the students. Really nice example to show it. Compact operators, ill-posedness of type 2, we all know. Integral equations, Volterra, Fredholm of first kind are the typical situation in L2 for having this. So now my philosophy of this talk series is ill-posedness can only occur in that form if the dimension of the range is infinite, because all finite dimensional situations have closed ranges. If you have a discretization, you have closed range, and you have no ill-posedness, but in practice you do not win. You have ill-conditioning, and this can be in the same manner. But in my theory, it does not occur here. Then the equation is ill-posed of type 2, if and only if A is compact. Well-posedness, however, does not include the case of non-injective A possessing non-trivial null spaces. That means well-posed in the sense of Neschet is also if the operator have a non-trivial null space. This is the specific thing. We will see this plays some role. I have a proposition. I will not read here the proof, but you have it in. Antonio will put the slides to the internet. If such a linear problem is well-posed in the sense of Neschet, then the equation is stably solvable everywhere on the range, which is a closed set. If this star is ill-posed in the sense of Neschet, then the equation is stably solvable nowhere. You have only yes, no, in all points. It's clear? This global property of the linearity. So in principle, for linear problems, this ill-posedness is rather clear. But this is the ill-posedness with respect to the image space, with respect to the y, not with respect to the x. Local well-posedness and ill-posedness, I recall this definition. We said we call such a nonlinear operator locally well-posed at some solution point. Now we are in the solution space. If there is a closed ball with radius positive, and there's some center in the ball, such that for every sequence in this ball, in the domain of the definition of the operator, the convergence of images implies the convergence of pre-images. That means if you are at such point x dagger, and there is such a ball, and you know you have here a sequence from, I call it xn, you know f of xn tends to f of x dagger, then the implication must be that the xn also go to the x dagger. This is local well-posed. And yeah, if not, then you have local ill-post. But you see, I'm in a radius. And what happens with the operator at other point? For example, you have a quadratic form, you have minus x and plus x. What happens with minus is not of interest for this. This is a very local point. And yeah, when we published this definition, people were very suspicious about this. And yeah, because local well-posedness requires local injectivity. That means if you have not local injectivity, you cannot have well-posedness. But my argument is this provoked criticism is not really clear in all points, because you can say the following. If there a real existing quantity is this x dagger, you want to recover it. And you have data, and the data go to the exact data. Then in the case of local well-posedness, you get this x dagger exactly. If the data get better and better, you come really to the right point. If there are solutions around there, you cannot get it. So the recovery of the exact element is really the recovery of physical quantities here. So it's a little bit, yeah, modeling, but I think the existence of this definition can be justified in that way. Now some proposition, let the operator be locally injective at some point. If the operator equation is stably solvable, then this equation is locally well-posed. This needs no proof. It's clear from definition. If you have local injectivity and you have stable solvability, then you have local well-posedness. But the implication is not, cannot be conversed in that way. The nonlinear operator can be stable solvable at some points and not stably solvable at other points. Similarly, the problem can be locally well-posed at some points and locally ill-posed at other points. And I have a couple of examples for showing this. For nonlinear problems, nothing is fixed. You have points which are well-posed in the range. You have points which are well-posed in the solution space. And so yeah, you can, very simple example. Such a function, all you know what happens there. You have a function which has here a 0, and then has such a tending to 0. This is 0. This to plus infinity, that's to minus infinity. And if you discuss this very simple form, you see the simple equation. This is really not in infinite dimensional spaces, but in R1. Is locally well-posed for all points here. However, the equation is not stably solvable at the point y is 0, because if you go to some yn which are near 0, you see the points can diverge to left or to right. So this is diverging effect, and you see the different kinds of stability are not the same in that way. Another example, self-integration weighted identity operator, a little bit constructed, a little bit academic, I think. Following way, you have L2, and you construct a multiplier. This multiplier is nothing but the integral applied to this function, and you see if n is the inverse of the 0, which means all x which are 0 here, then the operator is locally injective on x minus n and not locally injective at each point of n. And the corresponding equation is locally well-posed everywhere on xn, x minus n, but locally ill-posed everywhere on n. But the equation on the right-hand side is stably solvable everywhere. So you can have very, very different situations here. The last one, autoconvolution. You see it, our autoconvolution problem in this way as we have it. One can show that for this situation, all you know, the Titchmarsh theorem, very nice theorem. If we have a convolution of A and B, and the convolution is 0 on some interval, then A and B must be 0 on some interval, and the sum of the lengths of the intervals is bigger than the interval on the right-hand side. From this, you get that this autoconvolution operator has the properties that all such solutions, when they exist, the right-hand sides are compatible, then x dagger and minus x dagger are two solutions, and just two and not more, but only two in this way. And if the domain is the L2 itself, it was shown that this nonlinear operator is locally ill-posed everywhere. It's an interesting construction, but you need H alpha spaces there in order to show it. But if you can do the following, you restrict the domain to some elements from X alpha spaces, alpha bigger than 0, such that the norm is limited, some ball, then the problem gets better. You can stabilize this, and you get stable solvability in this way. I will skip this problem and revisiting the linear case again. For linear operator equations, which we have, such effects which we had in the examples may not occur. And there is a proposition. The linear operator star is locally well-posed everywhere on X if the equation is well-posed in the sense of Nash-it, 1, and moreover, the null space of A is trivial. That means if you need here local well-posedness, then you need more than well-posedness in the sense of Nash-it, but you need also a trivial null space here. If at least one of both requirements fails, then this equation is locally ill-posed. In that way, you can show it very, very simply here. So you have to distinguish these two types with null space characterization and without null space. There are some assertions which show this effect is nice. Again, the references, so I think it's late enough, and thank you for your extreme patience here, and thank you for hearing my things here. In Tuesday, who will be able could come on Tuesday then we will have real Banach spaces. Thank you.
Any questions or remarks?
Too late for remarks.
Well, see you next time.
Thank you.